Okay, so let's get started. So far in this class, we have talked about a lot of computer vision topics, but none of them are learning, right? None of them has the data aspects in it. Okay, so basically all of these are fundamentals, how do you do the filtering, how do you detect feature points, and how do you do matching, recurrent 3D, and so on. Right, so starting the fourth module, we will be talking about machine learning, basically how you can apply machine learning techniques to solve computer vision problems. All right, so starting from now, we'll talk about basics of neural network, basics of optimizations, how do you learn from data, and then gradually to talk about how we can design models that can understand images, videos, and 3D, and so on. Okay, so I'm sure that this will be maybe some overlap with some other courses that touch data science and machine learning, but hopefully this will be tailored specifically for computer vision. Okay, so before I get started, I want to kind of comment about final projects. So it's going to be similar to one of the similar as you can think about it as similar to homework, but it's going to be group based. So and then you can do anything, right? So this is an opportunity for you to explore any application, anything that you learned so far, and you can use any code base. You can do any application related to visions. Okay. So there, the kind of deliverable, you have kind of project report. Basically, you need to write like a 6-page of content, like including the results, right? So including the results, so it should be very easy to kind of filling out 6 pages. Your project report, we will post the LaTeX file for the kind of a template for you to fill in that report, and then you will have like a you can think about you present your work, right? Present your work, record a video that of you presenting your final project. We have like we highly encourage you to work in teams of 2 to 4 students, so that you can kind of explore, you can collaborate with each other. We could accept one-person team, but you have to talk with us. Okay, so like you have to let us know what the reason is, right? Maybe you I don't know, maybe you are working with some data that are sensitive, you couldn't share with other people, or you have been you want to work on this alone, or you couldn't find any groups. Okay, so kind of it's fine, but you want to we want to know why you don't work with teams. So the topics typically there are maybe 3 types of topics. I only list 2 here. Basically, one is that you think about any applications, right? So for example, you want to take an image and be able to read the text, right? So OCR problem. Maybe you want to read the license plate. You want to detect where the faces is. You want to be able to take an image and be able to detect a document so that you can rectify it. So it's a variety of different applications you can think about. So this is the opportunity for you to do that. And the second part is probably you take the state of the art and you try to stress test them, right? So take any state of the art on anything, maybe the structure for motion, maybe the feature tracking, and you try to test them on new data that you collected, you capture, and see what's going on, right? So observe, so that you can also learn what's going on in the frontier research is about. Probably the third one is a little bit more boring. It's mostly review papers and then compare, right? So it's kind of like a survey paper. So that could also be an option. Okay. Yeah. And the thing in the homework, usually we prohibit you to do, say, if you want to implement Lucas-Carnot, we prohibited you to just call Lucas-Carnot tracking, right? So it's obvious. Like if you use that, you don't learn anything. But here, basically, you can do anything, right? Maybe you can design so in the past, people have been maybe use their hand and be able to track their hand, and they can play Angry Bird without actually touching the keyboard. You can or people you can I don't know, for example, you can look at your person and you can detect and then based on the movement you can do something like count how many squats you have, how many push-ups you have, like maybe a fitness app, right? So any applications, and you can use any code base, right? So the simplest code base you could use is something like OpenCV. Okay, so it's very easy to use. Like you should just import OpenCV2. Then you have a variety of different functions that you can leverage. Right. So this is an opportunity for you to kind of explore any applications you are interested in, but you didn't have the opportunity to work on that. Okay. So that's about final project. Any questions? Good.
Is it about the original research?
No. It's not like it doesn't have to be original research, right? So yeah, but if you are original research, of course it fits this, but you don't need to be original research. I think the most fun project is mostly about building applications. Like so some you could just be creative. Some people are interested in maybe remote sensing. Some people are interested in art. Some people are interested in architectures. So you can take different domains and then build application now. That. All right. Okay, so let's talk a little bit about learning-based visions. So I think the research story comes from this. So there's around 2012, there's a ImageNet challenge. Basically, the problem is that I give you a bunch of training data of objects, right? So in the object class is 1,000. Basically, the evaluation is that if you train on this data, if I give you an image, then your method need to predict which of the 1,000 object this image contains. And at that time, that people like compete on this. So this is the error rate of the top 5 error. Basically, if your predictions, if your correct class is within the top 5 guesses, then it's a correct. So you can see that at that time there are multiple different methods, and the way people approach this problem is kind of extract C features and build some visual representation and do the classification. So at that time, it's not really good. You can see that different teams come up with similar. They all have kind of very bad, like so they kind of saturated. But so people have run this since I think 2008, and then it doesn't really work well. So people are kind of frustrated because the progress is not improving. And at that time, so vision people are kind of depressed. And then there's a team from Toronto kind of just rule everyone out of water, right? So they just push this cut error rate almost by half. And so computer vision people are really shocked, right? So like, and what's even more disappointing is that these is not vision people, right? So they are just machine learning people. They have no idea what computer, they don't know what C feature or all these other things, okay? So, but they are able to just leverage the machine learning models and kind of perform much better at the computer vision tests. So that moment kind of changed how people view the this deep learning approach to computer vision. And this is where the kind of the people, this is called, the first author is called Alex. And so it's called AlexNet. So sometimes you hear the AlexNet moment is at this December 2012. And since then, people that we are now in this wave. So AI has been up and down for some time. And right now we are in the third wave of AI. Like, but this seems, I don't know, maybe it's a bubble, but maybe not. So right now we are at this third wave, and it all starts from this. All right. So the key idea is the following. So on the left-hand side, you have this kind of images, and then you have traditionally what people did is that based on images, and a human needs to design what features I want to extract, right? Earlier, we talked about images, and we detect the kind of gradients, and we detect the seed features, and so on, and then kind of aggregate these features together becomes a fixed size feature representation for the entire image, and then we only train that classifier to make a prediction. What a deep learning approach, so this is called like shallow learning, because most of them are kind of hand designed. Like we humans think that we are clever, so we design, kind of think about what are the features that are good for the task. But what other people approach the problem is the following. So instead of having the human to kind of in the driver's seat, let's move, like let human just design the architecture, right? But the ways of these connections are learned. Okay, so all these convolution filters that we go way back to the second lecture, like those filters apply on this feature on these images, and they just concatenate them together. With between them, you have some nonlinearity, but that's basically you have this learnable filter, and you make the predictions. In the end, you train end to end. You based on the prediction, and you look at the ground truths and see whether they are similar or not. If they are not similar, then you will have a loss, and then we'll train all the way to this. Okay, and that's why it's called deep learning. And if you look at the existing that time, this basic architectures, and compared to the, it's not new actually. If compared to the what people have done in 1998 for digital recognitions, it's basically the same architecture, but it just scaled up. So this is where the convergence of using a lot of data and GPU and the deep learning. So algorithm-wise, all connect to each other, and that lead to this explosion. So it's not really about the algorithms get kind of so much better. It's mostly because that you now have the data, and you also have the computing power to actually train these models. All right, so it turns out it's very, very good. So compared to, if you look at if you visualize the feature extracted from these images, you will find that at that time, people just kind of amazed by how good these features are, like without human in the loop to design. And so these are the kind of the human design features. Each color indicates the different types of images. Maybe it's wildlife, maybe it's buildings, and so on. So you can see that human design features, they are all clustered together. They don't have a clean separations, which means that it's very, very hard to recognize images, right? To classify, oh, this image it belongs to the dog, this image belongs to a different class. But the convolutional neural network features, the learn features, is doing a much better job here. Okay, so this is early exploration. People are very happy to see this. And if you just look at the CNN features and just take the CNN features and then apply this on arbitrary tests, and you find that it gives you state-of-the-art performance on a variety of different tasks. Okay. All right. So all these are kind of pretty exciting. So we are going to talk about how the kind of the basics of these learning-based methods. Okay. All right. So if you think about deep learning, it essentially looks like this, right? So I'm sure that you played with Lego before. It's essentially a stack of some kind of linear transformation, okay, with some nonlinearity in between. So linear neural network essentially is a stack of linear transformations and turn into a nonlinear function. Okay, so we are mostly going to focus on linear classifier in this lecture, and we'll talk about how you can, what are the mathematics behind this linear classifier based on the input, and just directly try to make the predictions, and then talk about how we can optimize these weights. And then we will talk about, once we talk about how to optimize these weights, then if you just stack them together, you have a deep network. And then we'll talk about how, next time we will talk about how you can train a deeper model with something called backpropagation. Okay, so that's basically the plan. And then once we have these basics about how generally deep networks work, then we can talk about some specific design for images. So there we will talk about convolutional neural networks and transformer architectures. Okay, so that's basically the general idea of this module. All right, so linear classifier, the first thing is that there are a couple of kind of terminology that you want to remember. The first thing is there's something called score function that basically says that, okay, so I have an input X, maybe the X is an image patch, or in the entire image, or some kind of image features. Then you vectorize this image into a fixed dimensional size X, and you have a linear weight on top of that with some bias, and that is called score function. And this is called linear classifier because the score function is a linear function. Okay, it's a linear in terms of input. Okay, so now we have a score function. Basically, the score function basically give you a score, kind of how good you believe this instance is in class A or class B or class C. Right? Once you have the score function, you need to have a way to tell whether this is a good score function, which one of them is a good score function. And that thing is called loss function. You need to have a way to say, if I give you a W, you need to tell me how good it is. Okay, so people call it objective function or loss function. Okay. All right. So these are two key things. And there's another thing, it's called regularization. Okay, regularization basically says that if you only care about the fitting the data, then sometimes you will get something that's overfitting, right? So basically, you only care about the training data, but sometimes your solution space, the solution W, may not generalize well to others, and therefore you have some preference of saying that what kind of W, what kind of weight is better than others, right? So that's called regularization. And when we say that if we want to do the optimization, it means that we have the score function. We have an objective function that tells you whether this W is good or bad. Then we want to have optimization that says that, okay, if I start with some random W, random weights, what's the process for me to find a better W such that my loss function will be improving? Okay, so if I have this process, then I will be able to train a model. Okay, so these are the key kind of concept in if you take any machine learning courses, you'll learn this. Okay, question about this terminology. Okay, we'll use them throughout the course. All right. All right, so let's get something more concrete. So imagine that you have you want to build a cat classifier. Okay, so given this image, is this a cat or not? So what you have is, let's say it's an image, it's a 32 by 32, and you have 3 channels by 3. So in total, an image can be represented by 3072 numbers, right? So if you image, you can just stack them into a long column vector. Then you have this 3037. Okay, and you have a parameters. This linear function and this linear layers, linear classifier has some parameters. And by parameter, I mean something that you can tune. Okay, so think about the DJ board. You can say there are some tunable parameters that will change the output. Okay, so imagine that you are trying to predict a 10 classes. Then basically this is a function driven by these parameters, and that will give you 10 numbers. So more concretely, how you implement this in a linear classified case is that you will have this one, okay? So here the W is going to be a 10 by 3072 dimensional matrix, okay? All right, so it's a little bit hard to see what this looks like. So let's not work with this 32 by 32. Let's work with just 2 by 2 image. Okay, so imagine I have a 2 by 2 image, and you vectorize this, and then let's just work with the scalar kind of grayscale. So each image here, my 2 by 2 image, is just 4 numbers. Okay, and instead of working with 10 classes, let's work with 3 classes now. So you have here your linear classifier is essentially just a W times this guy, W times this X, with plus some scalar. That's the bias. That's called a B. Okay. So what this does, it will give you a sum score for each of them, each of the class. Okay. So this is the one kind of idea of linear classifier. And one thing that's interesting here is that sometimes people write in this way, like a transformation, linear matrix with this guy, and then plus the bias. But it's kind of annoying to write this in 2 terms, like Wx plus B. So you can actually just augment these guy, this vector by adding a 1 in the end. You get something like this, right? So it becomes like the new weights. It's just you can merge the B bias into the weights, so it's become easier to write. You just a linear transformation is just Wx, okay? But here the W include the bias itself. Okay, does it make sense? All right, so see, okay, so. All right, so you can look at this. This is a kind of this is one way to look at this is one way to look at the linear classifier. Basically, you have some input, and then you do the dot product between this guy and plus a bias. You get a score. This is kind of how you compute the method. Okay, but you could also think about a different viewpoints, right? So you can think about this is basically the same as taking this image, and then you have a weight and a weight, and directly do the element-wise multiplication and add them all together, right? You can also think about the weights like are like this. So the reason why you want to do that is that now you can visualize what the weight looks like. Okay, like that this weights, you just instead of representing it as 1 by each row as representing as 1 by 4 vector, you can represent this as 2 by 2 vector. All right, so what does that look like? If you look at this visually, if you train on 10 classes, and this will be what would the linear classifier look like if you look at this. Okay, so you can see that car classifier, it will look like something kind of maybe this red car mostly. So you will look at if your images correlate well with this kind of shape, it will have a high score. And you can see that the bird is basically something that is greenish color around the background, and then something darker in the middle. So it captures a very rough idea about what the class is. Okay, so horses, you can actually see a horse shape here. Sheep has a green, the blue background. Okay, so these are just different interpretation, right? You can think about the linear classifier Wx plus B as just pure kind of algebra computations. You can think about this W is a kind of like a template, like template that compare with the canonical class. And you can also think about W plus B is a line in this image space, right? In there, the image space is very high dimensional, like a 3000 dimensional vector. But here, the W plus B, that will give you a score that will give you kind of, it's essentially a cutting this visual space as a plane, right? as a kind of a plan that cuts through this. So hopefully that the visual space here, then this guy will if this is the I don't know, airplane, they will have a high score. So essentially your data lives in this space and you try to cut through the classification in this way, okay? By cutting up this this visual space. So you have these three different types of interpretations. Okay. Okay, so questions so far? Okay, does it make sense? All this good? All right, so now, so this is just a one linear layer. Basically, you have some input and you have a linear transform to give you output. And the output here is the multiple class. You have multiple numbers, okay? So, but you need to, but how, the question is, how do I find that W, right? How do I train a good, right now it's just arbitrary score function. It's just that if I give you a random W, I have a random classifier. But what I really want is that I need to find a good W. And the way we need to find a good W is that we need to have a way to tell us whether a W is good or bad. Okay, so the idea is that we need to kind of tell whether this W is good or bad. And here the key idea is that we have some data and then we run this current W and give you the score, right? And so here you can see that some of them are already good, right? For example, this guy is like 6 it's already correctly classified this well. Some of them, this 2.9 is already classified this well. But sometimes some other things is not doing well, right? So how do I do this? So basically, we need to have a loss function. We need to have a function that if I give you a different W, it will give me a different number, right? Tell me how good or bad this W is, this parameter is, right? So that's a loss function. And then we need to have a way to optimize that loss function with respect to the parameter W. Okay, so this is the optimization process. Okay, so we need to have a loss function, and then we need to have a way to optimize. So these three things together, we can set up a machine learning problem. So we have a score function that tell me if I give you some parameters, I give me a scores, and then I'll have some way to tell what's the good parameters. That's a loss function, and we have a way to optimize it. Okay, so these are the three main key concepts in machine learning. So let's say if we have this, again, like simplify this, we have three examples, and we want to predict, we have a classifier that predicts 3 classes, and these are the current scores, okay? So a loss function essentially is that it's a function of parameters, okay? So I give you parameters, the parameter will give me the scores, and the goal is to come up with a single number that summarizes how unhappy you are, right? Based on the training examples, okay? So basically the idea is that you want to summarize how unhappy you are. Okay? So one way to, there are multiple different ways in the classification setting. The most popular ways are 2 ways to summarize how unhappy you are. For example, here, if you look at this example, this cat example, this example representation is, if you intuitively, this doesn't look good, right? Because you predict the car class is 5.1. but you predict cat only 3.2. So that doesn't look good, right? So you should be unhappy about this prediction. And this one, you should be already happy about this prediction, right? Because it's already predicting this well. So you don't need to change much change your weight. This example doesn't need to change too much about your weight. And this guy, you should be super unhappy because this guy, it should be a flock, but your current classifier, current linear classifier predicts something that say that it's 2.2 as a cat, 2.5 as a car, and minus 3.1 as frog. So whatever your objective function, it should capture the level of unhappiness about these predictions. Okay. And once you do that, your job is then try to make this happy. Okay. Question about the high-level intuitions about this loss function. Okay, so the first type of way to look at these things is the following. So it's called there's a particular name. It's called hinge loss. That says the following. It means that sorry, they should look at this. Okay, it means that my prediction should be my loss looks like this. If the correct class predictions, let's say in this correct class predictions, and if a correct class, this guy is a correct class, is the car. If your score for the correct class 4.9 is larger than the other class predictions by a margin, for example, the margin is 1, then your loss is 0, which means that you already are getting the correct prediction, and the the score for correct prediction is already larger than other classes by a margin, by 1. So which means that you don't need to do much about that class and already. In this case, 4.9 is already larger than 1.3 and 2.0 by a lot margin. Then you pay a cost 0. Basically, the loss function is very happy that your classifier is doing a good job for this example. Okay? But how do you quantify the unhappiness of other incorrect corrections? So the idea here is the following. You want to compute the score for other class minus the correct class plus 1. Okay, so basically, if your prediction is the correct one, then it becomes larger than the incorrect classes by a margin. Then you are paid 0 cost. Other than that, you get some more costs. Okay, so let's walk through an example here. All right, so if you look at this example, what the loss function looks like this. Okay, you should take this guy, the 3.2. It should be max of 0 between because it max out it should be take 5.1 minus 3.2 plus 1. Okay, so this guy is going to be 0. Plus the other guy, right? 0 minus this guy says that it's okay. So ideally, you want the prediction for the cat to be higher than the car, but it's not. Right? So ideally, you want this instead of 3.2, you actually want them to predict at most 5.1 plus 1. Right? You want to be larger. Okay? But it's not, and therefore you need to pay the cost. The level of cost you have to pay is 5.1 minus 3.2 plus 1. Okay? So that is the cost you need to pay. That's this example, you're not happy with this, the behavior here. And for the flock here, because 3.2 is already larger than minus 1.7. So you can see that in this case, you don't need to pay a cost, right? So you have this 0. So this cost overall, at this example, your loss is 2.9. Okay. All right. So this is basically the idea of hinge loss for SVM. So here is an example. If you do the calculation, you'll find that the 4.9 is the correct class, the score for correct class, and it's already larger than the other class, the incorrect class, the score for incorrect class by a margin of 1. Then you are happy with this, right? You have 0 loss. So, and we work with this guy, you'll find that it's really bad because now the score for the correct class is only minus 3.1. And you need to pay a cost here, right? So you need to pay, let's say, it's not correct for the cat class, it's not correct for the car class as well. So you need to pay a total of 12.9. Okay, so if you add it all together and then average, you get the cost of 5.27. So this tells you how unhappy you currently are with the current parameter W. Okay, does it make sense? All right. Okay, so let me go through this. All right, so and this, if you kind of want to implement this, it's basically like this. It's very simple, right? You have this, you take the scores with the dot product with the input, you get a score, and you take the margin and you compute the sum of the margins, and that's basically it. All right, so this is just one type of loss function, and this is a different type of loss function that treat this that's probably more common these days, that treat the score prediction as a probability distribution. Okay, so here's the one, it's called softmax. Okay, so you probably, if you go into deep learning or language models, you'll see this everywhere. So the key idea is that I want to make this guy as kind of a probability, right? Based on the scores, I want to see what is the probability of prediction as this image is a cat, and the probability of this guy, the other one is a car or a frog. Okay. So how do I make this a probability distributions? Okay, over probability distribution over the classes. So the way we do this is the following. We first, because these scores could be, you're just taking a dot product between a matrix and a vector, and it could be positive and negative. So how the first step is to think about how can I, because probability distribution must be positive, right? You shouldn't have negative, there's no such thing as negative probability of a certain class. So you need to first make sure that every element is positive. Okay, so you basically just think about this and think about a function that can take arbitrary input range between negative and kind of, it could be arbitrary negative or arbitrary positive, and get something that's only positive. All right, and that particular function people usually do is to take exponential, right? Just think about exponential, what exponential did. If I have an exponential of minus something, it goes to kind of 0, right? If you exponential something positive, is positive. So exponential function is always positive, no matter the input range is, right? So now what we did is that we take this scores and we exponentiate it with each element independently. We get something that's all numbers are positive, right? And this is called unnormalized probability. And then what you do is that, but you want to interpret this as a probability. So what you need to do is that what's the probability of if I have a probability over 3 classes? What's the probability of that it must enforce for you to call this as a probability distribution? You have 3 classes. Yes. It has to add up to 1. Yes, exactly. So how do I make these 3 numbers add up to 1? And what's the process? What's the operation I need to do? Divided by total, right? So I need to sum them up and divide by that sum. Okay? Yeah. So that's exactly what we did, right? So this is just the softmax is just this. Okay? Take individual elements, exponentiate it, and normalize it so that they sum out to 1. Okay? Right, and that becomes the probability, right? So you can see that it's 0.3, 1.3, and 0.87. Okay, and this guy is minus, so it becomes like it's almost nothing. So it kind of probability. It is still a positive probability, but it's just small. Okay, All right. So there's some way to measure the difference between two probability. That's called the KL divergence. But I don't have time to go in deep into that. But basically, what you have here is that what you can do is that to measure how well like how unhappy you are, what you do is basically do the following: is to take the correct class, this particular number, and just take a minus log of that number. All right. So just think about this intuitively. That's your loss. Okay. So that loss looks like this, right? So if you imagine that this guy is close to 1, right? If this probability is close to 1, what does that mean? If you have log 1, then that becomes log 1 is 0, right? Then it means that you are very happy with this, okay? But if this guy is, for example, is a low probability, which means that it should be the correct class, but you're predicting a low probability for the correct class, which means that you're doing a bad job, right? So in that case, the minus log of this probability will capture this effect, right? It will quantify how unhappy you are. And in this case, it will say, oh, this is a 2.0. Okay? So this comes from the fact that you are measuring the KL divergence between the correct probability 1, 0, 0, that's the correct class, and the predicted class. Okay? All right, so I have a video about that, so I can point you to the video about like what KL divergence actually is and how to actually compute it. But basically, what I want to say here is that this is another way to compute a loss. Okay. All right. So basically, you have these type of like a linear classifier. So now we complete 2 pieces, right? We first have a linear classifier, a linear score function. That is just you have some input, you have a weight, you have some metrics and vector and bias that will give me 3 numbers. That's 3 classes. For each class, you have a score. That's a score function. And you can supervise, based on that score, you can say, okay, what is the, you can use different loss function to quantify how happy you are. Okay, you can either use SVM-based method or use the softmax-based methods. Okay? All right. So the next question, the final missing piece is that how do we optimize these things? Okay, so now imagine that you have a classifier, you have some training data, you train this model to make a prediction on your training data, and you can quantify how unhappy you are if I give you random W. But now the question is how can I find a good W? Okay, so that's a core idea. So the core idea here follows the concept of imagine that this is the kind of landscape of the loss function, and your solution is in your 2D position, and the height of where you are is how you are unhappy with that. Okay, in order to be happy, you need to get home. You want to go down the hill. Okay. But you don't know the full landscape of the entire loss landscape, right? You don't know every places. What you do know is that the locations of where you stand, okay? So what will be the strategy if you want to get home and leave the mountain? Any idea? You only see, like, let's imagine that you are in a heavy fog. Right? How do I get home? Any idea? Yes. Follow steep direction, right? Basically, kind of greedy approach, right? So I want to get down. So the idea is that I want to make sure that at this location, I want to find where is the directions. I don't want to go up, right? Otherwise, I I will want to find the direction that I can move downward. Okay, so I can leave this. So that's the basic strategy. The whole deep learning, all these advances you are seeing is basically this core idea. Like you have a loss function and just let's follow the slope. Okay, and in one dimension, you learn that in your kind of freshman or high school calculus class. It's just the Greek derivative, right? So you want to find the derivative. Numerically, it looks like this, okay? So imagine that your current W, the current W is just a vector, right? So your current weight has some vectors and that has some loss. So how do I compute the derivative of each individual dimensions? Oh, it looks like this, right? So remember that in calculus, what we did is that if I perturb each one of the dimension a little bit, then I can compute how much the loss change, right? So you will do this sparring. So take this guy and perturb this a little bit, then give me this will give me a little bit of change of the loss, right? So I get this and basically take the difference between the loss and then divide it by the step size, and that's my gradient. Okay, and you do this for every steps. Okay, you compute this, you change each dimension a little bit and see what the loss change, right? And this will tell me how well, if I move along this direction, this loss will increase, how much this loss will increase. So this is the idea of numerical gradient, right? So you basically kind of just manually add this each dimension a little bit and see what the outcome looks like. But this is bad because it's very slow. It's only approximated. What you really want is to get something that's numerically accurate. That you want to get a closed form solutions. Okay, so that's typically what we want. And so the overall algorithm looks like this, right? So I have a gradient descent algorithm. Basically, I started with the initial guess. We first have some initial guess, and then I compute the gradients. I compute a gradient. Basically, if I move this certain way, then how much loss they will increase. And here, what's interesting here is that you will actually take, but you don't want to take a too large step size. So you will have a step size that control how much you update your weights. Okay, so you'll have this step size usually is kind of small number like 0.01 or something like that. Okay, and then you will move along the negative directions, not the gradient. The gradient tells you where you will increase the loss, and because you want to decrease the loss, so you move along the negative directions. Okay. All right. So basically, that's the gradient descent. And one of the main, there are many different methods out there. So I'm going to spend some time to talk about how these different methods works and how they are related to each other. Okay. All right. So that's actually the main part of this particular part. So you can think about this the third part. Like we now have a score function. We have a loss function that tells you how well the parameters theta is, and so now the optimization, the role of optimization is to find a good theta, right? So I want to get a outcome, the learn theta as output. Okay, so how do I do that? So think about this, right? I have a space of parameters to explore, and every parameters will give me a loss. Right? I give you a loss, and let's say your loss is like this, okay? So what you really want is to think about this as but initially I don't know what's a good parameter, what's a good model parameter theta here. I don't know. And I couldn't really try out all the possible theta, right? In one dimension you can do that, but imagine that you have like thousands of dimension, right? You couldn't really find that. So all you have access to is that kind of as like initial and randomly, and you want to improve this iteratively. And the way you improve this iteratively is that you think about, at this point, I look at the slope. In this case, the slope is negative. If the slope is negative, which means that I will improve the loss if I move the x directions. If I move in the x directions, right? So basically the idea is that it just locally compute the slope and then move along the negative directions. So over time, you will kind of gradually move toward the local minimum. Okay, so that's basically and you're happy with this, right? So you minimize the loss. You find the parameters that can minimize the loss. And since the loss tells you how good your model is, this must be a good model. Okay? All right, so we call usually this algorithm called graduate student descent. All right, so let's see how we can do this. Okay, stochastic gradient. So start with something very, very simple, right? So here you have, let's say you have, like previously we have just one parameters only, like just theta. But what if you have two parameters? So you have a W1, that's one parameters, and you have a W2, two parameters. And again, every pair of parameter will give me a loss function, a loss value. Okay, you tell me how well I'm doing. So let's start with this. At this location, I don't know. Again, I'm kind of blind. I don't know which W is the right one. So obviously, here you can see that the center is a good, like the dark color means that you have a lower loss value. Okay, so here we have this initial parameter here. So how do I find a better? How do I find the update this initial point so that I get a better solution? So the way we do this is that since we don't know where to look for, all we can do is to look neighborhood. For example, in this case, we look at this point because we have loss function. We can compute the gradient of this direction. And this gradient of this direction it's a 2D vector right now, right? And this 2D vector has two components. One is the x direction. That is the derivative of the loss function with respect to this W1 parameters. And you also have the vertical direction. That is the derivative of the W2. Okay, and together, these two together tells me the direction where if I move along these directions, I will increase the loss. Okay, that's what that's what gradient mean. Okay, so far so good. All right, so now how do I update the gradients? How do I update my weights? So that's my initial parameters. What I want to do is define. So I have this weights that's new. I want to update this, right? So the new parameters should be because we know that it's the old parameters here, and we know that the gradients along these directions. Basically, if I move along this direction, it will increase the loss. So the best thing we can do is to move along the negative direction, right? And move toward these directions. So I want to do this, okay? Take the W1 minus this guy, okay? But because the gradient sometimes is large, and you can imagine that if you kind of just directly minus this guy, because your gradient calculation is only based on local regions. Your loss function could be very complex. So that's why you want to add something that's small number. You don't want to move too far. Okay. So you update your first parameters W1 in this form. You also update the second parameters in this same way, right? The new parameter of W2 is W2 minus this gradients multiplied by the learning rate. Okay. All right. So then what you do is that you don't want to kind of write, if you have a millions of parameters model, you don't want to write this as a million equations, right? So usually what we will want to do is to represent this as a vector, okay? So here's how it works. You just represent this as a vector, right? So you have the new, the original gradient, original weight is W1, W2. You update the gradient by taking this guy minus the alpha times the gradient directions. Okay, so this is the multi-dimensional case. So I'm showing the two-dimensional case, but in the case of billions models with billion parameters, it's the same, right? You basically write this down as a vector. All right, questions about this? All right, so just label this. This is the updated parameters, theta t plus 1. So we start from 0 and gradually update this guy. And this is the theta t, this current parameters. And here, this is the learning rate. And this guy is the gradient. Okay, so if you look at the general form, it looks like this. All right. So it's a vanilla version, so it works well for this simple setting. Let's see what it looks like. Okay, basically you start from, let's see, let me play this again. Start from that initial point, and you will optimize this. It will become like gradually move to the optimum. Okay, so it seems that we're done, right? So this just works. Okay. But the problem is that it's not that simple. The loss function usually do not behave like this. The loss function could have a different shape. Okay, so let's look at what will happen in this shape. Okay, so here you can see that the loss function is pretty sensitive along the W2 directions. Okay, so you can see that if you move this W2 a little bit, it will change rapidly. It's not sensitive in the X direction. Right? So X direction is basically similar. So let's see what happened if you just run the gradient descent here. Okay, this is what happened. So you will take forever to converge, right? You will still converge to the right solution, but in this case, you can see that because it's not sensitive to it's very sensitive to the y directions, to the W2 directions. So the gradient descent will basically just kind of oscillating in this loss function. Okay, so it will take a long time to actually make progress to converge. Okay, so that is the problem. So how do we solve this? How do we kind of address this problem? Like for general loss function, we would really want to make sure that my optimizer to update my weights to be robust to these kind of things. Okay, so the key idea is the following. So let's observe what the gradient looks like from different parameters. Okay, so if you look at the gradient, so I'm going to plot the W1 with respect to the weights of W1 and the loss, the gradient of loss with respect to W2. Basically, it says that if I change W1 a little bit, what would the loss will look like. Okay, so you can see that from the W1, it looks like this. Okay, so what does it tell us in this case? It shows that the W1, the gradient over the direction of W1 is more or less consistent, right? The value is the same, where the gradient for W2 is very oscillating. It's kind of positive, negative, right? Because you are jumping back and forth. Okay. So here comes the idea. So if you observe these things, what we can do is the following. Instead of trying to just use this gradient alone, because you know that some parameters, the gradient will be oscillating, become positive and negative, and some are consistent. So what you can do is the idea of using momentum. Okay, so here's what the strategy is doing. What they do is that you just compute the moving average of like basically you start from this gradient start from this velocity start from 0. So for some dimension, because the gradient is consistent, the same directions. Like basically, you think about this, I'm walking, and then every time I check the gradients, the gradient always tell me to move this direction. So what should I do? I'm very confident that this is the direction I should go. Then I will pick up momentum. Okay. So in this case, I will move faster if I say that if all the gradients along that direct dimensions always tell me to be moving to that directions, then I will pick up speed. Okay. At the other hand, if the gradient, if every time I check the gradients, it always be oscillating. Okay, sometimes positive, sometimes negative. It's oscillating. It means that if I compute a weighted average over time and through these things, it will get canceled out. So it means that I will move less oscillating along the y directions. Okay, so if you just change this, it will look like this. The output will look like this. Let's see. Okay, so now you see that it moves faster along the x-axis, and y-axis it reduced the oscillations. Okay, reduced oscillations. Right, so just see the difference with momentum and without momentum. Without momentum, it only look at the gradient itself. But if you just compute a weighted average over the gradient history, that becomes your velocity, then you can find a better solutions. Okay, so this is the idea of stochastic gradient descent with momentum. Questions so far? Yes.
On that second grade, overshot it.
Yeah. So we're going to talk about another way to handle this. The momentum method, the drawback is that it will overshoot, right? So sometimes it pick up momentum this direction, but it sometimes take too much and it will overshoot. Okay, so that's the problem. So this is one idea of using momentum. Basically, look at the gradient statistics over time, and you can use that. Instead of using the gradient, you use the gradients. You use the velocity as the update method. Okay, so now let's go back to the stochastic gradient descent. So another way to make an observation is not to look at the gradient itself, is look at the gradient magnitude. Okay, so here what you find is that the gradient magnitude here along the x directions and y directions. So then let's see what that looks like. Okay, again the same setting, but now you plot the gradient magnitude, like how large the gradient is for the x direction, and the gradient magnitude for the y directions. All right. So what you observe is that this gradient magnitude is very small. Like along this direction is very small, and so which means that you should kind of try to normalize this, right? If the gradient magnitude is small, then you want to boost up the speed. Okay. And this gradient magnitude is very large, right? You can see that they move very far away. This gradient magnitude along that direction is very large. So, which means that if it's too large, I want to suppress the magnitude, the gradient there. Okay. So here's the idea of the things. You can think about this is that I want to have two different learning rates for different dimensions. For the x directions, I want it to be faster, right? And for the y direction, I want it to be slower. Right? I want to normalize this learning rate. And the way we do this is the following. I take the gradient magnitude and compute a moving average of that. Basically says that historically, this dimension has a large gradient magnitude. What does that mean? It means that it's oscillating a lot. And if it is oscillating a lot, I want to make sure that the learning rate for that dimension is smaller. Okay? So here you can see what I'm doing here is that I compute the over an average over time about the gradient square gradient magnitude. And then what I did is to take this divided by this guy. What it means is that if certain dimension, the gradient magnitude is small, then I will take the alpha divided by a small number, which means that I will increase the gradient rate for that dimension. And if the dimension, some dimension, for example, the y direction, the gradient magnitude is very large, then I will divide by something large number, I will have a smaller learning rate. Okay, so that is basically, you can think about this as a way to normalize different the learning rate for each individual dimension. Okay, and this idea is called RMS plot. Okay, so let's look at what this looks result. You can see now even for this way, it's very smooth, right? It's directly go to the solution very easily. Okay. All right, so now we have two good ideas, right? So the first one says that it's a momentum. Basically says that if I observe the history of the gradient itself, and we can use that to update my model. The second one is this guy says that I have if I observe the gradient magnitude, the second, the square of the gradients, if the gradient magnitude is large, then I should divide by I should make the learning rate small, and if the gradient magnitude is small, then I should divide it by that, so the gradient becomes the learning rate becomes larger. So usually you have these two ideas. What's the next thing you will do? Any idea? You have two ideas that they're all they all make sense. What's the idea? What's your idea? Yes, combine them. Yes, exactly. So so here is the visual picture of what happened in 2014. So basically, that they look at these things, and on one hand, you have a good idea for momentum. On the other hand, you have a good idea for RMS plot, and you just combine them, and then you get the method called edit, right? And that's very simple, right? And it turns out this is going to be the method for training any deep learning models. Okay, it's just simple combination. All right, so here's what it looks like. You have these gradients. Again, you maintain the moving average for the gradients. You call them a velocity, and you also compute the moving average of the square gradient, kind of basically how large the gradient is. Then your update is super simple. You just take this guy and you combine these things, right? You combine the learning rate but use the velocity, right? Two ideas combined together, then you're done. Okay? And yeah, just simple idea, but this guy gonna get gazillions of citations because of that. All right, so usually for people, this is a kind of the default parameters. How do you update the kind of moving average for the beta 1, beta 2, and so on? Okay, and you want to add this epsilon because the numerical stability. Okay, so but there's some tricky thing. It's not like that immediately obvious. That is, you have this initialization part. Your velocity and the square gradients are 0, right? You don't know what the gradient is, right? Initial training, you don't know what the gradient is, and therefore, what you will need to do is to correct. There's a corrections pi. Basically, if you directly use this, you will find that this gradient will be very slow. The update will be very slow because your initial v and the s is very, very small. Okay. So from some math, what you will do is that you know you need to bias correction. Okay, you need to take this term so that you can update this guy. So initially, if the v is some number, because you know that this guy initially is 0, so you need to divide it by that 1 minus beta is 0.9, so you need to multiply by 10 to correct the initial bias. But other than that, it's basically the simple method of combining these two together. Okay? So you use the bias corrected version to update this. All right, so this is all great, but what people found is that it's very robust, but in terms of performance, sometimes the SVD plus momentum still perform better. So people wonder why that's the case. And what people found is the following. So if you go to literature, what you find is that people usually, the loss they have here, they don't necessarily only have the data term that's only feed the data. They also have some kind of regularization term. Regularization term basically says that my parameters, I don't want the parameter to be too large. So I have a regularization term like this. So what happened is that if you directly do this, if you compute a gradient with the regularization, and you computer ADAM algorithm, you will look like this. Okay. So what happened here is a weird thing. This term will have a weight decay, will have a regularization. But what happened here is that if the gradient magnitude is very large, then you should have more weight decay, right? But if you compute a gradient in this case from this combined loss, what happened is that your weight decay, your regularization will also be weighted, which means that if your gradient along that direction is very large, then this guy, the learning will become very small. Then you have a less regularization. So it's kind of contradicting. So here's again a visual story about this phenomena. So you have a large weight, you change that dimension, change a lot, and so you have a large ST, and you just screw up yourself, right? And then you have less like regularized version. So what you really want is to not have this, right? So one simple fix is the following. So is that you just don't compute this guy. So this is called ADAM-W. You just remove this guy and just regularize this directly. As opposed to compute this. It's just a simple fix. And this is called decoupled weight decay regularization. It's basically ADAM plus a W. And if you look at, it's very simple, but if you look at right now, if you look at any of the machine learning models, 99% of them will probably use ADAM-W. So you can see all these papers are using ADAM-W. So this is really the state we are in machine learning literature we have right now to train deep learning models. Okay, so you all understand this? All right, so I'm running out of time. So next one, I will talk about how you can stack this. Like right now you have the concept of score function, loss function, and optimization. Now, next one is that how to stack them together, and then we can design models that can understand images. Right, thanks.